All right, let's get started for the third lecture. Second lecture today? Third lecture of today. I arrived in the middle of the day, so I'm confused. For the third lecture of the day, we've got Brian Swingle. Very happy that he agreed to give 3 lectures on complexity and black holes. First one today is complexity.
Great, thanks. Nice to see you all again. And yeah, so I'm going to talk over this week about the 2 subjects here, complexity and black holes. You've already heard the word complexity mentioned several times this morning, so we will talk more about those kind of notions later on. The plan I want to follow is to start with complexity first, so sort of quantum information, qubits, that sort of thing. This will give the other lecturers some time to build up the ADS-CFT machinery, which I can then take advantage of. So next time, today will be complexity, next time will be black holes and their conjectured relationship with complexity, some of those things. And then the final lecture on Friday will be about recent results where you can actually prove rigorously in various kinds of models that complexity should grow linearly with time. Okay, so I'll discuss how the sort of inspirational ideas that came out of this meeting of complexity and black holes gave rise to a lot of work in quantum information that you can now establish some versions of these conjectures for certain kinds of models. And I'll describe all of that in detail later. So as with everyone else, please ask questions at any point. And the plan for today is complexity, but I want to start out just by very quickly motivating the basic idea. And so we've seen this picture several times now. Actually, people have mostly been drawing Penrose diagrams in flat space, but I'll draw one in ADS. And this picture, which will be explained in much more detail in the later lectures and tomorrow by me, is a picture of 2 entangled quantum systems, a left system and a right system, and which that entanglement is expressed as a geometrical connection between the 2 sides. So for example, this is a time t left and this is a time t right. And if you look at the moment of time 0 on both sides, you can cross this space-time along that line. And that's some sort of spatial bridge or wormhole which connects these 2 sides. If I roughly sketch the geometry of this outer region, which is anti-de Sitter space, and similarly this region, that bridge at time equal to 0 looks like something like this. So this is just, you start out near the boundary where space is large, you come in to this special point where space is minimal, and then you go out again, right? And this, as we'll learn in later lectures, I think, is related to entanglement between the 2 sides. In particular, this surface here, the area of this surface, computes the amount of entanglement or the amount of entropy that one side has. And the story of complexity is the story of what happens, one of the starting places is the story of what happens if we advance time. So suppose we go up to, say, this time, and we look at some characteristic spatial surface, say, or cut through this picture. And we can ask, what does the picture of this spatial slice look like at later time? And the rough cartoon is that it looks like the outside part, now with a long tube connecting the 2 pieces. And the length of this tube is roughly proportional to, say, the time that you've evolved on the 2 sides. And the key puzzle that led to a lot of this thinking, I would say, starting from a paper of Hartman and Maldacena and then really emphasized by Lenny Susskind, is that this growth of the interior happens for a very long time, long after other things stop happening. So long after the black hole from either side, or for a variety of simple probes, long after the black hole looks like it's not really changing anymore, this geometry continues to grow. And so there's a real question, which is, what is the meaning of this growing interior of the black hole? What's the physical meaning of that growth? And the conjecture that I guess really Lenny Susskind put forward, based on essentially tensor network ideas at first, and much refined since that time, is that this growth of the interior represents a growth in complexity of the quantum state dual to this entire structure. Okay, so somehow as time evolves, that state becomes more and more complex. Nothing obvious is changing after a certain amount of time, but still it's a pure state whizzing around in Hilbert space doing something crazy. And it's becoming, in a certain precise sense, more complicated. And the idea is that the growth of the interior here is a picture, a physical picture of that growth in complexity. This can very literally mean that essentially there's no more efficient way to prepare this state than to start, say, here and simply evolve in time. There's no shortcut which takes many fewer operations to get there, right? And this has all kinds of very interesting and profound consequences. It predicts, for example, that at very late time, maybe this growth should stop because complexity has to saturate at some point. And you can ask, can you see that in general relativity? What would be the physics of that? And people have looked at that, and we'll discuss it. There's also all kinds of questions about, well, complexity is usually something that's very hard to diagnose in quantum system. So how can we be seeing this complexity growth behind the horizon? There must be something weird going on there. This has led to discussions of pseudo-randomness and the extended Church-Turing thesis. We'll talk a little bit about that as well. But the basic idea is this picture led to the conjecture that the complexity of this state grows with time. And these lectures are about explaining, first of all, a very precise, somewhat arbitrary, but precise notion of complexity. So just to give you a very sharp sense of what we're talking about, that's today. Then explaining this conjecture in more detail and the different formulas that people have cooked up to sort of quantify this growth of the interior. And then on the final day, we will try to actually prove that this growth happens in some special class of models. Not an ADS-CFT, but something inspired by ADS-CFT. Okay, so that's where we're going. And as I said, if you have any questions, please feel free to ask anytime. Okay. So as I said, today we're going to start with kind of the qubit side of things. Qubits plus circuits. And to start, we want to start with a single qubit. Okay? And it's very standard to describe that single qubit via a certain special basis called the computational basis that we label as 0 and 1. Of course, as in quantum mechanics, you can have any superposition of these two basis states, so any such state is allowed. But we often refer to this special basis, which for my purposes I'll take to be the eigenbasis of the Pauli Z operator. So if I apply Pauli Z to this basis, then I get -1 to the A, and here A is again 0 and 1. Right? Yeah. Is there any connection between growth of the interior and the Hartmann-Moldesena surface in this picture? Yeah, they're definitely closely related. And we'll talk about that next time, actually. So just save your question for tomorrow. But yes, this Hartmann-Moldesena surface lives sort of not on this particular, if you say define this as a maximum volume slice, it's not quite the same slice, but it's a similar structure. And yeah, so the fact that entropy eventually saturates has to do with the fact that these boundaries are getting further and further apart. Yeah. So we'll discuss that more next time. Other questions? Okay, so we have our single qubit. This is kind of the elementary unit of computation. This is like a quantum version of a bit. And we have this Z operator. Now we can also consider what are called quantum gates, which are just unitary transformations that act on these qubits and transform the state of them. So if, for example, we think of 0 and 1 as like logical 0 and logical 1, that's the idea, then we could, for example, consider the NOT operation, which would take 0 to 1 and 1 to 0, like that. And at the quantum level, I could implement that via the Pauli X, right? So if I apply the poly x operator to 0, I get, let me write it here. Poly x operator on 0 gives me 1, and poly x on 1 gives me 0. This is just the familiar fact that for qubits or for spin halves, x flips the spin from up to down. And of course, the magic of quantum is that any superposition, when you apply this gate to it, just passes through, right? You have linearity of the action, so you get alpha 1 plus beta 0. Okay. You can consider other kinds of single qubit gates. This is not enough to generate every single qubit state, right? Because all we're doing so far is flipping 0 and 1. So we could also, for example, rotate about the z-axis by some amount theta. And the action of that on these basis states I'll define like this. It just gives you a phase on those states, like so. So just track the notation. This is the exponential minus I, so it's a phase. Theta is like an angle. And here, this A is either 0 or 1. So what it says is that it takes the 0 state to e to the minus I theta over 2, and it takes the 1 state to e to the I theta over 2. So it's just a relative rotation of phase of these two states. And if you go into your basic physics, what this would correspond to physically is rotating the vector on the Bloch sphere, say, in the xy plane by an amount theta. Okay. There are other kinds of transformations, like something called the Hadamard gate, which is like a basis transformation between the x basis and the z basis, which we can write this way. And these are not all independent. In fact, you can, for example, take this Hadamard gate along with the z rotation and use it to produce an x. So for example, if you take any state A, you apply Hadamard, then you rotate about z by an angle of pi, and then you apply Hadamard again, this becomes A plus 1. And here I'm doing addition modulo 2 because this is logical data. So 0 plus 1 is 1, and 1 plus 1 is 0. Okay? And now I want to introduce a nice pictorial representation of all this, a quantum circuit, which looks like the following thing. We have a notion of time that I'll imagine goes from left to right, looking at the board, and you have some kind of initial state, for example, A. You draw a line, which is like the world line of the qubit, and then you can do various things to it, right? So for example, you could apply x, in which case what you get out is this state. Or you could, say, apply Hadamard, in which case what you'd get out is this state. And so on, right? And then we could represent this identity as the statement that, say, this circuit's where I apply Hadamard, then I rotate by pi, and then I apply Hadamard again, that this is the same as doing my NOT operation, right? And as always, I don't keep track of the overall phase. That's not really important to us. And these are all examples of quantum circuits. Okay, so they're just a nice pictorial way of representing the action of these elementary operations on our single qubit. There's a little bit of a funniness here because these are often drawn this way, but then the equations are written the other way, so you have to be a little careful about not getting that too messed up, but it's usually not too bad. Okay. So now we've done one qubit. That's a little straightforward. Let's do more than one. We can do many qubits. And the first thing we need to do is figure out a nice basis. So we just use the computational basis again, but now repeat it over all the qubits. So we can imagine we have a bunch of arguments, A1 through AN. This would be the computational basis for n qubits. But this long state vector is very cumbersome, so this is where the quantum circuit language really saves us a lot of effort. And one thing we can certainly do is, say, have 2 qubits. Maybe they start in the 0 state. And we could certainly apply single qubit gates to each of them separately, right? So we could apply Hadamard to this one, and maybe a Z rotation of some sort to that one, and that would output some state, right? In this case, it would be like that. And the final state would be a tensor product, or more generally, a sum over tensor products of these things. But the real virtue of this notation is that we consider gates that act between the qubits, interactions, right? So for example, one thing that we like is something called control not. That's, if we had not before, control not is a gate that, depending on the value of some control, applies or does not apply not to the other qubit. So we draw that like this. A, B. The solid circle indicates the control. So this is the control. This is called the target. And what's being output here, if this is the basis, A and B, what you get is a state at the end, which is A, and then A plus B. Or let me write it this way, B plus A. Doesn't matter. So in other words, A stays unchanged, it's the control, but depending on whether A is 0 or 1, you either add 0 or 1 to B. If you add 0, nothing happens. If you add 1, then you flip it from 0 to 1, and vice versa. Okay, now this is all great. Why are we doing this in the first place? Well, I gave you the motivation here, but from a more quantum information point of view, what's the point? The point is that in nature, we have access to certain simple ingredients, right? You can fairly easily produce lots of photons, and you can, by coupling those photons to atoms, arrange some sort of elementary interactions between them. And these are the things that we have access to in the lab. We can't necessarily immediately generate some arbitrarily complicated transformation of the photons. We have to do it using these elementary ingredients. And so complexity and these circuit pictures are all about how to build up complicated general things from simple ingredients. And now, of course, what simple ingredients you have depends on the system that you have, right? Maybe in certain kind of lab implementation, it's easy to rotate about the z-axis, but not the x-axis, or maybe it's easy to do C0 or some other kind of different operation. So one question we have to ask, which we'll address in a second, is does it matter exactly what gates I'm using here? Does it matter that I focus on Hadamard and rotations around z or rotations around x? What if I do C0 versus something else? Does that change anything? And the answer will be that if the gates are of the right type, it doesn't change anything very essential, but it will change the details of these pictures. But the basic have some privileged set of elementary things that you can do, and you want to ask, how do I construct kind of arbitrarily complicated things out of those elementary ingredients, right? And again, just emphasize like what you consider basic depends on the physics that you're thinking about, right? But just as with this example here, where we could make the not in two different ways, like you could imagine one kind of system where the not operation is something elementary that you can do, say by turning on a magnetic field for a certain amount of time. Or you can imagine it's not something you can do easily. Maybe the only thing you can do are Hadamards and rotations, but then you could still generate not effectively, right? So let me give you an example of a more complicated circuit, which starts from this controlled not and does something else. What if I wanted to do a controlled rotation by angle theta? How could I do that? The C here indicates control, so this would be a circuit that you would draw like this. This is the control line. This is the rotation by theta. So suppose I don't want to view this as one of my elementary operations. I want to understand how to build it out of these other ingredients. Maybe C naught is easy for me to do, and I can also do these 1 qubit rotations easily enough. How can I make something like this? Well, you can play around with it. It's a fun thing to do. Here's one way to do it. If you consider the following circuit, let me write it down, then I'll explain. So this is a circuit in which you first rotate the lower qubit by an angle theta over 2. Then you do a controlled not from the first to the second qubit. Then you rotate by the opposite angle. And then you do another not, another controlled not. So what is this doing physically? If I wasn't have these control knots here, this would simply rotate and then unrotate. So nothing would happen, right? And in fact, that's something people did in the 50s. It's called spin echo. There's a way to apply evolution for some amount of time, then apply a certain specific operation, and then reverse that evolution, and you come back to the same state again. So what we're doing here is sort of a state-dependent spin echo, where based on whether this first qubit is 0 or 1, we can stop this cancellation from happening. So we first rotate, then if the first qubit is 0, the controls don't do anything, so nothing happens to this line. We simply rotate back, and then we get nothing at all, right? So we've done no rotation at the end of the day. But if this upper line is 1, then what happens? We rotate by half the amount, then we switch 0 and 1. You can easily convince yourself that's like rotating by opposite of the angle. That's the spin echo. So this becomes effectively plus theta over 2 instead of minus theta over 2. And now they add up instead of subtracting, and you get overall a rotation by theta. Okay, so this is just one example where if I imagine that controlled knots and single qubit rotations are the things that are easy for me, the elementary operations, I can, by composing them in various ways, build up more complicated structures. There's one other gate I want to mention, which is called the control knot or Toffoli gate. It has the following structure. It involves 3 qubits now, A, B, and C, all on the computational basis. And now the output here, well, I don't do anything to A, I don't do anything to B, but if both A and B are 1, then I flip C. I apply not. So it would be C plus, one way to write it would be A times B in this mod 2 notation. An interesting fact, actually, is that this gate by itself is universal for classical reversible computation. But the reversible 1 and 2 qubit classical gates, not and C naught, are not, actually. But there is actually a way to write this Toffoli gate in terms of these elementary ingredients. You need at least 5 C naughts. That's a fun paper from some years ago. But it is possible to write this 3 qubit gate entirely in terms of C naughts and 1 qubit gates. Right. It's not possible to do only with classical gates, actually. You need to rotate phases, but with quantum gates. And in that way, you can produce this 3 qubit object. Right, so this is also called C naught because it has 2 controls. And in fact, we'll see in a second that it's interesting to consider these gates where you control on lots of different things. Yeah. Yeah, you have to give yourself the microphone.
Yeah, just trying to understand the lingo. When you say that the gate is universal, you mean that you need to include it in a universal gate set?
Well, yeah, when I say a gate set's universal, I didn't define that. I'll define it in just a second. I mean that just gates from that set are enough to generate any operation or any state.
So in classical computation, you do need to include this one, and in quantum, you don't. That's the...
Yeah, in classical computation, like the 1 and 2 bit reversible gates are not actually enough, but quantumly it turns out that they are. Just a fun fact. It's not nothing deep, I don't think. At least I don't know how it's deep. Okay? Yeah, question?
No worries. This is maybe a pedantic point, but when you're defining a set of minimal gates, are you going to choose like one fractional rotation, or like, because RZ of theta is like a continuous set of gates.
That's right.
Are you just going to pick one, and that's going to be?
I'm actually not. I'm going to allow this continuous fam, but I'll discuss this in a second.
Okay.
Yeah. Yeah, that's a good question. So let's talk now about the notion of universality. So let's consider the following gate set, which is any single qubit operations and any pair of C naughts. Let's say, let me put it this way. Any C naught with arbitrary control and target. So consider that. Imagine you can do any of those things. That's actually pretty reasonable. For example, the C naught you can get by turning on, suppose these qubits were represented as spins in some system. The C naught you can get by turning on a ZZ interaction for a certain amount of time. And the single qubit operations just amount to exposing the system to magnetic fields in various directions for various periods of time. So you simply expose it for however long you want, and that length of time will determine the angle of the single qubit rotation. So it's a quite reasonable thing to allow. And with this gate set, we have the following claim. This is the definition of universality. Any state can be exactly produced from these gates. Meaning there is a circuit built from a finite number of these gates, which produces any quantum state I like on however many qubits I like, starting from, say, the all-zero state. And for this purpose, of course, it's essential that I allow any single qubit operation. I need this continuum. Otherwise, I couldn't exactly prepare all states. We'll come back to this in a little bit, but that's an important thing because the space of states is a continuous had only a discrete set of transformations, I could potentially come very close to different states, but I wouldn't necessarily be able to make every state exactly. And this is called universality. So we would say this gate set is universal because it can make any state you like with a finite number of steps. Okay? We can also address the question, what if I use a different gate set? Well, as long as the gates of that other gate set can be written in terms of these gates, then that other gate set will be totally sufficient for my purpose. So any pair of universal gate sets are equivalent in the sense that you can just write the gates of one in terms of the gates of the other, or vice versa, and therefore translate any circuit in terms of one into a circuit in terms of the other. So this is the sense in which, at the level of information processing, it doesn't really matter whether you're talking about photons, spins, or NV centers, or whatever. As long as you can do these operations, you can prepare any state. You could sort of mimic the physics of any other simple system in terms of these elementary operations. Yeah?
Usually in complexity theory, you define universality in terms of the set of computations that you can perform, so arbitrary computations. Is that equivalent to saying you can produce any state you want? A computation here being thought of as a map from the set of all possible states to the set of all possible states, so that's a bigger set than the set of states. So could you explain the relation between those two notions of universality?
Yeah. Here you might call it state universality. You could talk about computational universality or unitary universality. They are related. Like, for example, we can consider unitaries encoded by applying them to a Bell pair with some secondary system. So then we can make that state implies that we can make this arbitrary computation as well.
So just the point of confusion I have is that the set of possible maps from n states to n states, or from a state space with n basis elements to n basis elements, seems much bigger than the number of states.
Sure, yeah.
So for that reason, it's not obvious to me that being able to make a set of states from 0, 0, 0 is as complicated, and therefore that the same gate set would be universal.
Yeah, I see what you're saying. Yeah, so here maybe let me emphasize that I can do this for any number or variable number of qubits. And so there is a state on twice as many qubits that is equivalent to a transformation on just n qubits. And so in that way I can get around this objection. So it's like I have a family of structures that nest in a nice way, and I can produce anything in that way. I mean, you could also just prove an analogous statement about the unitary directly without too much trouble. Yeah, there's a question here.
Thanks. So let me see if I understand. Is this statement saying that starting with any n qubits, I can produce any other state, pure state with n qubits, or that starting with an arbitrary number of qubits, like are there states of n qubits for which I need 2 n qubits to produce them?
That's a good question. No, so I'll sketch a procedure to do this, just using the same number of qubits. It is possible that you can do it faster if you allow arbitrary numbers of qubits. So for example, there are recent constructions where if you allow exponentially large number of extra qubits, you can prepare things very rapidly in a certain sense, but of course you have to address exponentially large number of things. So depending on what you consider hard or easy, this may or may not be a useful thing to do. But yeah, I'll show you a procedure just in a second where you just use the same number of qubits to make any state.
And can the control and the target be the same qubit?
No, I would say we normally make them separate, yeah. I haven't thought about whether it would make sense to do that.
So just as a follow-up, so I thought that when people write algorithms, like they just take like the Clifford gates plus like one fractional phase.
Yes.
Is that equivalent to this? Like you clearly can't get to any state, but is that like an equivalent statement that you only need that set of gates to do a certain set of computations?
Well, there would be an analogous statement like you can come within epsilon of any state you like, and you can make epsilon as small as you like. So of course you can't produce every state if you have a discrete set of gates, but you can get arbitrarily close to every state.
Okay.
Right. Okay? So let me just give you a sense. This is actually relevant later, but let me give you like one very Baroque construction of how you can produce these things. So let's talk about a proof of this claim. Let's do it inductively. So the starting point is that I can produce any single qubit state. Here's one way to do it. Start from 0, do Hadamard, rotate about z by an arbitrary angle theta 1, do Hadamard again, and then rotate about z by another angle theta 2. As a nice exercise, you can show that this will produce any single qubit state. Roughly speaking, the first angle tells you where you are from the z-axis on the Bloch sphere, and then the second angle gives you the amount in the xy plane. Okay, so we can make any single qubit state. That's the starting point. So let's suppose that we can make any n-qubit state. That's our inductive hypothesis. And now let's write down the most general possible n plus 1 qubit state. Let me write it this way. Alpha psi 0, 0, plus beta psi 1, 1. Technically what I'm doing here is a Schmidt decomposition where I decompose the full quantum state on n plus 1 qubits into a state on n, which is correlated with state 0 on n plus 1, and then a state 1 on the first n, which is correlated with state 1. And I extract out the amplitudes out front. And moreover, from my hypothesis, I know that this can be written as U0 on 0 tensor n, and this can be written as U1 on 0 tensor n. For some circuit, that's my hypothesis from step 2, because these are n qubit states. So I can make either of these separately via some circuit. And now maybe you see the idea. If I could somehow apply U0 and U1 in a controlled fashion based on the value of this extra n plus first qubit, if I could do that, then I could prepare this state. So here's the idea. Let me use this one. Let me draw it as a circuit. So let's start with alpha 0 plus beta 1. That we know we can produce as an input. And then let's have a bunch of other lines that are all in this 0 state. So if I can now do the following thing, if I can apply a control U1, right? And then let's suppose I flip the value of U1, 0 and 1, and then I apply a control U0, and then flip back. This would prepare at the end of the day my target state. You agree? Because all you're doing is, this is saying if you get value 1, then you apply U1 to these remaining qubits. And then you swap 0 and 1, and you say, if now I'm 1 again, I apply U0. But now I've swapped effectively the control from controlling on 1 to controlling on 0. So this U1 is applied to the branch of the wave function correlated with 1, and U0 is applied to the branch correlated with 0. And there I produce, at the end of the day, my full state here. And so the proof goes through as long as I can construct these control operations. But actually, I already told you how to do that. We know how to, C0 is a basic gate. I showed you how to construct controlled phase. In fact, you can control any single qubit operation. And I also showed you this Toffoli gate, which is a controlled control knot. So that's controlling on the value of control knot, or controlling the control knot. And so you can actually prove, sort of, again, inductively, by iterating these control operations, that you can produce any amount of control you like, again, from the same gate set. In fact, this naive argument would suggest that these like many-body controls may have exponential complexity themselves, exponential number of gates in them. But there is actually a more efficient circuit that only does it with, I think, linear number of gates. So with a little lemma that you can construct Cu in the set, or from the set, provided you can construct U itself, then it immediately follows that U1 and U0 were circuits in our gate set, and from this little lemma I can construct the controlled versions. They have a certain amount more gates in them, but they can be made from the same basic elements, and therefore I can make any state that I like. Okay, so that's like, this argument was actually given in a paper, I don't know, maybe 20 plus years ago, a famous paper in quantum computing. I don't know exactly how long ago it was, I forget. But anyways, this is the kind of thing you would go through to establish rigorously that some set of gates can produce anything you like, right? Is there a question? Okay, and now that we know that, we're finally prepared to define complexity. So let's talk about complexity. This will be exact and state complexity. And the complexity, I may call it C0 of any state, psi, is equal to the minimum number of gates needed to produce psi. This thing is called the reference state. This is called the target state. And this, as I said, is the complexity. In this case, it's exact, and it's a complexity about states, not about operations. Right? And since I showed you just above that you can make any state, this is a well-defined notion, right? And moreover, as a little exercise, you can go through this procedure, do it sort of recursively, building up more and more of the state by using the Schmidt decomposition over and over and over again. You can convince yourself that there's a bound which says that C naught for any state psi is less than or equal to some constant to the nth power. So it can never be bigger than exponential in this construction. Essentially, you need to produce all 2 to the n phases. Each of those phases costs no more than a sort of fixed amount of gates or a polynomial number of gates. And so you can bound the whole construction by this.
Excuse me, I'm wondering, gates here, that doesn't mean that it's only involved with this C0 and single qubit gates, or it can be any
Yes, that's right.
Okay.
All I'm doing is single qubit rotations and C naughts.
I see. Okay.
That's actually sufficient to produce any quantum state, and no more than an exponentially large number of...
Because if one allows themselves to use other gates, maybe it's faster, right?
Sure, yeah.
Okay.
So indeed, we should emphasize this depends on the gate set, it depends on the target and the reference. Here I'm requiring exact complexity, I exactly produce the state. It depends on all of these things, right? If you use a different gate set, you can put upper and lower bounds because you can write the gates of your first set in terms of the second set. So you know it won't ever take more than some fixed amount. But yeah, it could have substantial savings. And the thing to keep in mind, maybe from a physicist's point of view, is this is the kind of stuff that's talked about by complexity theorists and computer scientists for whom the relevant thing is polynomial versus exponential, for example. So they're not too concerned with whether the complexity is 5 or 5n or 10n. They want to know if it's n or e to the n. That's sort of the more relevant axis on which they often think. But as part of this story, we've spent a lot of time, I mean the community has spent a lot of time thinking of sort of more precisely about exactly what the complexity should be and whether it has a precise meaning in terms of its coefficient and so on. Yeah.
Is that definition of complexity a good definition of a metric, like in a math sense, like a distance? Like for example, is it 0 if it's the same, or like is it symmetric? Is it like a triangle inequality thing?
So far, I only defined the complexity of a single state relative to like essentially relative to the zero state. So yeah, you can talk about like relative complexity. So how much gates does it cost to go from one state to another state?
I see. Okay.
And then one way to do it would be to just reverse back to 0 and then go out again. But there can of course be a more efficient way to do it, right? Okay. And so we need to define and discuss that kind of definition to talk about metric.
Okay.
But you can't do that. You can't think about that.
Thank you.
So let me just also mention a notion of smoothed complexity or approximate complexity. Because this is, in some sense, a nice definition, but it's very fragile, right? Like I could have a state that's very close in some physical operational sense to the target, but it mixes in a very small amount of like a Haar random state, and then the complexity might be very high. And that's maybe not physically what we care about, right? Because we have finite precision in all our measurements, so it doesn't matter if there's some tiny, tiny fraction of something very complicated. That may not be super physical. So we can define instead a C epsilon, which is maybe something like this. It's the minimum over all states phi with the property that phi minus psi is less than epsilon of C0 of phi. So basically we look at all the states that are nearby our state in some physical sense. Maybe this is a trace distance, so that means there's no measurement that can distinguish them with probability greater than epsilon. And then we ask amongst that ball of states around our state, which one has the smallest complexity. And that's a more smooth definition that says we can throw away very small pieces of the state that we don't care about operationally. And then you have this more continuous object. And this is also something that will be more robust if, say, you allow only discrete gates versus continuous gates. Then you might still think that this is a well-defined notion, whereas the exact complexity might be infinite for essentially every state, because you need an infinite number of gates to truly reach any particular quantum state. Yeah, there's a question in the back.
Is there a canonical way of knowing how many minimum, like, in what order and how many minimum number of gates are needed to produce some given gate?
Can you say again? I didn't catch the first
Some
part.
canonical way of knowing what's the minimum number of gates. It may happen that someone constructs a gate, but turns out there's a more efficient way of constructing it from the universal set of gates. So is there a canonical way of knowing this?
If I understand the question, I would say no. I mean, we just pick a gate set, and then by definition, that's the things we can use. So there's no notion of like there being a more efficient version of that. It's just those are the elementary ingredients, and what's the minimum number of those that we need to produce our state.
Right. Okay. So for example, are there multiple different ways of constructing a given gate using the same set of universal gates?
Sure, yeah, there can be many ways.
Exactly. So and is there a canonical way of knowing what this minimum number is? Or like today, people think it's like, oh, for this particular gate, we need 10 of these like universal set of gates, but like universal gates. And tomorrow, there's some cleverer way of coming up with a smaller number, and now the complexity of that gate decreases.
I don't think so. I mean, I may not be able to tell you what the complexity is, but I don't think it changes from day to day.
Right.
I don't necessarily know what it is for any particular state.
So if I give you some gate, would you know, like, is there a canonical way of constructing that gate from a given set of universal gates?
Not that I know of. Like, we can fix a procedure, like the procedure I gave here, which will produce one circuit.
Right.
But I don't know if there's, I wouldn't say a canonical way of doing it necessarily.
Okay, so if there's multiple ways of making the same sort of gate using these universal gates and there is no canonical way, maybe someone might come up with a sort of inefficient way of constructing a gate and define the complexity that way, but like, turns out there's a more efficient way of doing this using lesser number of gates. That way the complexity of a given gate might decrease.
Yeah, I just want to emphasize the complexity is a minimum. So it's a minimum over all the ways that you or any other person in the future might come up with doing this.
Right, so it may change.
So best we can do is, no, it doesn't change, it's a fixed thing, but you only typically ever give an upper bound on it. And someone might have a better circuit later
Okay, good. Okay.
that gives a lower complexity, and then, okay, they have a better circuit.
Upper bound, okay.
Yeah, but whatever it is, even though I can't calculate it, is a well-defined object.
Is there a way we can define the lower bound?
Yeah, we'll discuss that in a second.
Okay,
Yeah.
thank you.
Yeah.
Just to comment on that, I thought this is one of the difficulties that in many cases you have algorithms that are pretty good, but you don't know if there's a better one.
Sure, yeah.
And it's very rare that you can actually prove that you found one that cannot be improved.
Yeah. Yeah, this is, I mean, especially at the level of exactly which order the gates are in, that's like something we don't ever think about because it's sort of so detailed. It really rarely matters except in some very specific cases. You know, like if you're trying to produce the fastest fast Fourier transform, then maybe you think about this. But apart from that, like, it's not something that comes up a lot. Yeah.
So in light of what Jeff said earlier, it seems like thinking about smooth complexity in the context of black holes can be a little risky because in that case, maybe there can be a very small difference between the state and lead to a huge difference, for example, in the entanglement. Is that something you're going to talk about later with black? Like, smooth complexity seems nice now, but maybe there's a...
Maybe there's a monster lurking?
Yeah, I don't know.
Sure, it's possible.
The definition Brian is using of the states being close is like the states actually being close, not just they look similar if you look at some matrix elements.
Yeah.
So that's like real.
Okay, awesome. So like actually similar states. Okay.
It really depends on what our notion of closeness is. So for example, in physics, maybe we just care that like the 1 and 2 body expectations are the same. And then, yeah, I wouldn't have any kind of, we could be missing a lot, right? But if it's really there's no measurement, however complex, that can distinguish these two states, up to probability epsilon, you know, then, yeah, it's probably capturing this.
Good, thanks.
We got 2, so, yeah, go first, yeah.
What happens if in the allowed gates you allow all the 1 and 2 qubit operations?
If you allow all 1 and 2 qubit gates.
Yeah.
Yeah, it's still universal, and the complexity will be less because you can produce certain things. Certain things count as elementary now that previously you had to construct.
But the bound, for example, is still polynomial? Or?
I'm not sure what bound you're referring. Yeah, oh, this bound, yeah, it's still exponential, yeah.
Just to clarify one point. So when talking about universality, we made this claim that any state can be exactly produced from this state, from these gates. When we say this, we mean with finite number of gates, or it can be infinite number of gates?
I mean finite number, but the gate, I'm still cheating some infinity in there because I'm allowing arbitrary continuous parameters.
Yeah, so like if this is like arbitrary continuous parameters and if there is some gate in the gate space, if there is some state in the state space for reaching which we need infinite number of gates, isn't that like we will never reach that state practically and it is not universal? Isn't it contradicting the thing?
Well, I would say it's really like there's a very precise procedure where imagine time is infinitely divisible. There's a precise procedure that takes no more than exponential time, where for each rotation of single qubit, you just apply a field and wait for some bounded amount of time, no more than 2 pi over the field strength, and you can rotate however much you want, and that's a compact direction, so you don't need to go forever. And then for these 2 qubit gates, you do the same thing, but with some 2-body interaction. So physically, this guarantees that you can produce the thing in a finite amount of time. Now, if your timing is not precise enough, then you won't get exactly the state you want, but the physical time is actually finite. Okay, and there's a precise, it's just turning things on and off in the lab, essentially. That's like the real, more or less the real thing you would actually do.
I see, thank you. But even for continuous states, I mean, so technically speaking, there is no way to make a universal set using which we can actually eliminate the infinity even in possibilities.
I'm sorry, I didn't catch the last
So,
part.
I mean, for the continuous system, it is not possible just to include some new kind of gates using which we can actually exclude the infinity from a possibility.
Yeah, I mean, just because the states are continuous, you always need some continuous thing. But with a discrete set, you can come quite close to various states.
Thank you very much.
I mean, to all the states. Oh, was there another question?
Yeah, I have a question. I might have missed this, but in that definition of complexity, are you minimizing also over the possible set of universal gates, or is it defined based on one specific set of universal gates?
Yeah, I just picked a set. I picked a set.
Okay, so can that tell you something completely general, universal about complexity that then you can apply in a DSFT to black holes or something like that, or do you need also to minimize over the set of gates to do that?
Well, I would say there's 2 answers to that question. Answer 1 is if, as I'll discuss tomorrow, there are conjectures in ADS-CFT, complexity equals something, like equals sign, not tilde or whatever. And for that to really be true, you would need some very precise, specific, tailored definition. Maybe such a thing exists, and we'll discuss that a little bit tomorrow, but it's not clear. But on the other hand, for some other purposes, like this growth here, as long as you fix a gate set, like maybe you don't allow arbitrary gates in your gate set, this growth will always be there. Maybe the rate of growth will be different, but the growth itself will persist. And so in that sense, the complexity is capturing a robust property of the system.
Okay, so in terms of variation of complexity, okay, but if you want to define, say, an absolute value of complexity with respect to some reference state, in that case it seems like, say that with one set of gates you have a polynomial complexity, and with some other set maybe you have either a much smaller polynomial or, much larger polynomial or maybe an exponential complexity, then it seems like that feature should be captured by some different feature of the spacetime, right?
Yeah, I mean, it could depend on what you want to choose as your basic gates. But if they're similar in a certain broad sense, it won't matter more than a constant factor, typically. But, anyways, I'll talk more about this.
Thank you.
Okay, so yeah, just to maybe emphasize what these questions were pointing out, can we define there's a question. Can we define a separable state as a state having finite C0? Well, they all have finite C0, actually. I show that it's actually bounded by this number. So in this definition, every state has finite complexity. It could be very large, but finite, if the number of qubits is finite. But yeah, separable states are special in that they have like no more than n complexity, or maybe 3n, because we could produce any single qubit state via these 4 gates, right? Hadamard rotation, Hadamard rotation. So that means any state which is a tensor product of single qubit states, you could produce with no more than 4n gates, right? So anything which has, any product state would have, say, a bounded complexity given by no more than 4n, for example. Okay, so let me.
When the complexity is small, then the set of states that have that complexity or less is going to be measure zero, right, in the full Hilbert space. Do we know if all but a measure zero set of states, if you're working with exact complexity, just have the same complexity? It feels plausible to me they do, but maybe that's too naive.
Yeah, it's a good question. I'm not sure. Why don't you repeat your question?
The question was whether all but a set of measure zero states in the full Hilbert space have the same entropy, have like, entropy complexity. So, yeah.
But complexity, you mean exponential?
I mean exact, they would all be exponential, it would be very high. Yeah, we would expect with the definition of exact complexity given here that it's definitely measure zero for some fairly large time. And these arguments about proving linear growth are basically, yeah, well, it's about showing that the codimension grows in a linear way, in the obvious way. I'm just wondering if it just does that until it suddenly becomes codimension zero, and then all the states except that measure zero have the same complexity.
My question is, you might have expected that almost all states in the Hilbert space are in some sense pseudo-random, and thus almost all of them are somehow exponential complexity, except for some set of measure zero. So again, that's adding to what Jeff is saying, okay, so finite, some small, except for some finite measure, some small set, and that leads to a flip question regarding this smooth complexity. Clearly, if you pick epsilon large enough, then all states have polynomial complexity because you just pick epsilon to be, let's see, the max of the min distances from every state to the nearest state of polynomial complexity. So you can pick a choice like that, and then it's clear that everything is polynomial. So there must be something that's involved. So my question has to do with, for some sets of choices of epsilon, there's an interesting answer you get here regarding this. And so what are those choices of epsilon? What's known about that, if at all?
I think to have your one, you'd have to have epsilon very close to 1. As the dimension gets large,
Yeah. I would expect that, but I'm just, there must be a theorem about
Yeah,
this,
I mean,
and I don't know what the theorem is.
It depends on what you define as close, I guess. Like if it's trace distance, yeah, probably you need pretty generous margins, I would guess, because you allow arbitrarily complicated measurement, and those can do a lot of distinguishing. But if you say only allow computationally bounded measurement, then you might think you can get away with a pretty lenient epsilon and still you're close to something simple.
Yeah, I think if epsilon is fixed and you take the Hilbert space dimension large and your measure of distance is just trace distance or fidelity or anything like that, then by state counting, most will be exponentially complex. That, for any fixed epsilon, that's to be true. Yeah, exactly.
Yeah. Okay, good, excellent. So, oh yeah, I guess I'm done, right? Or no, I go till 4:30, right?
Yes, 1/2 past. Yeah.
I mean, I can stop, yeah, but. Okay. So in the remaining indeterminate amount of time, I want to give you some examples, okay? This has been very abstract, so let's just, like, what do we actually know about this, like in some real down-to-earth qubit systems? And in particular, I'll give you essentially lower bounds. So these are like ways of, if you like, witnessing or testifying that there's some amount of complexity in your system necessarily. How would you know that? And, not surprisingly, things like lots of entanglement or, a high degree of effective randomness are the kinds of things you can use to guarantee that your system has a lot of complexity in it. Okay. So let me give you an example starting out with what is called in the literature a trivial gapped phase of matter. Let me define it in a somewhat funny way as follows. What's the physics intuition? A phase of matter is trivial in the sense that it has a Hamiltonian which produces a ground state. If you can adiabatically deform that Hamiltonian such that the ground state becomes a product state, no entanglement, then we say it's trivial. That doesn't mean it's not interesting physically. Diamond is a trivial state of matter from this definition, but diamond is very interesting and important. But it's just about a question of how much entanglement is in that state, essentially. And trivial is, in this sort of phase of matter sense, just means that it's adiabatically equivalent to a product state. Okay. So one way to formalize this is to imagine you have a Hamiltonian, in fact, a family of Hamiltonians, h of lambda. Lambda lives in, say, 0 and 1. H of 0 has a ground state which is given by 0 tensor n. And H of 1 has a ground state given by your physical state. So in other words, imagine some material where the particles or degrees of freedom are sort of more or less localized, but not quite fully localized. By turning down some interaction or turning up some potential which confines these particles to their site, you can deform the system into a limit where there's no entanglement, no correlation, no motion between different sites.
So by this definition, any field theory with a perturbative expansion, let's say the standard model or something, would it be trivial because you take the coupling to 0 and then they're all a product in momentum space?
No, I mean, okay, here I'm using a real space basis.
Right, but then it's a basis-dependent statement which you
Yeah, it's a basis-dependent statement.
Oh, it's a basis-dependent statement.
Yeah, I'm choosing it to be this particular reference state. And if you choose a product state in momentum space, that's actually related to this via, like a linear depth circuit. So you would have a pretty different answer in principle.
Right.
But this is a notion that captures, like, so for that example you're talking about, you have both, you have, say, a scalar field theory, which can have both a gap and not have a gap. So it fails to capture, that definition fails to capture the fact that changing this gap would result in a quantum phase transition where thermodynamic properties were singular as a function of some control parameter. So it fails to capture that, but this definition would, in the sense that if you have two states that are both trivial, you can deform between them without encountering a quantum phase transition. So there is some physics to the choice of this spatially local basis, which is not present, I would say, in that example. If you're using momentum basis, because that you can close and open the gap without changing the amount of entanglement, which is 0 in this free particle system.
Doesn't it feel uncomfortable to have to make a basis-dependent statement?
I'll just be honest. I sympathize with your view, but it doesn't make me uncomfortable.
Okay. Fair enough.
I mean, in particular, the fact that it seems to capture phase transitions in a nice way makes me pretty happy, actually. It kind of excites me. I really like it. Okay. Now, it turns out that this example is equivalent to the following statement. I'll be a little bit rough here. State psi is related to state 0 by a finite depth circuit. That means the following thing. Let's start with all zeros. Here, that's the ground state of H of 0. This is these world lines. And now what I can do is apply some circuit, which looks like this. I'm being very schematic here, where I apply some series of, say, 2-qubit gates, or 1 and 2 qubit gates, it doesn't really matter. And what I produce at the end of the day is capital psi. Is the target state. And here, this number of layers equals the depth d. And the rough idea of this is that you simply evolve adiabatically with this h of lambda, starting from 0 and going to lambda equals 1. So via the adiabatic theorem, you can approximately prepare the ground state of h of 1 by starting with the ground state of h of 0, evolving adiabatically. And then you need to turn that evolution into gates, which you can also do using something like trotterization of gates, right? And that's an approximate statement, but you can dress this up a little bit of fanciness and produce an exact statement where this finite depth statement is not literally true, but sort of morally true. There's a little bit of epsilons, which I'm happy to tell you about offline, but I don't want to get into here. But the moral of the story would be that these trivial phases are related to product states via finite depth circuits. And so the complexity of such a state would be less than or equal to some number times the depth times the number of qubits. Precisely because we have this path in Hamiltonian space that can take you from the trivial state to this let me put an epsilon here because that's important for this to be technically true. We can go from those all zero states to the target state via this finite depth circuit, which is basically doing adiabatic evolution of this gapped Hamiltonian. So you can see actually in sort of response to Vijay's question, the adiabaticity is actually closely tied to, and the fact that I'm doing spatially local things is tied to the fact that I have a local Hamiltonian in real space, and that's kind of why it makes sense physically. Yeah, question?
What's the meaning of finite here? Because I thought you said that the number of gates to get from any state from a reference state is bounded exponentially. So is exponentially not finite in this case?
I've forgotten what I said when I said finite. But here what I mean is constant, proportional to n.
Okay,
and finite depth means the number here in front is not scaling with n.
Okay, so that's kind of finite.
So it's way better than exponential.
Okay, it's especially finite.
Yeah, it's especially finite. Yeah, I like that. Yeah, another question here.
Does the concept depend on an epsilon?
Yeah, I'm being a little bit careless.
Can you repeat the question, please?
Yeah, so the question was, does the constant, this number here, depend on epsilon? And the answer is, in principle, yes.
So if you pick an arbitrary.
Yes, you can bound it. You can bound it. And there might be some weak independence, like it might be a log n or something like that. But yeah, it's not too. Vijay has another question.
Great. So all agree. I just have one question. This is coming from ignorance. So when people build quantum computers, they can certainly do, of course, local operations using stuff. Is it possible to conceive of doing operations, for example, momentum space? Because photons, if you think about them as waves operating on things, you could be working actually in momentum space?
Yeah, I think it's conceivable. In particular, for example, in trapped ion quantum computers, the way they implement the 2-qubit gates is by coupling the internal states of the ions to the collective motion of the crystal, and then coupling back. So they actually couple to normal modes, which are doing some sort of global thing, and then coupling back. And in that way, they actually sort of natively have long-range gates. Like they can have, this spin talk to that spin over there because they're coupling via the collective modes of the crystal, of the Coulomb crystal. So there are platforms where it's more natural to have at least sort of non-local operations. It's not quite momentum space, I would say, but yeah, that can be a thing. Yeah. Interestingly, like the blow up from this is never more than linear in n because you can always just take any local gate and swap it around to anywhere else. So even a non-local circuit will only ever buy you a factor of n at most in the complexity. Okay, another example is a CFT ground state. So this is now not trivial. In particular, it has long-range correlations, power law correlations, and you can, as an exercise, convince yourself that in a finite depth circuit like this, you could never produce power law correlations between arbitrarily well-separated objects, effectively because there's a light cone which says that information that starts here propagates a finite amount out and won't propagate arbitrarily far away, so you could never establish such correlations. So you would need a longer range circuit to do that. And so actually that's one example of a sort of complexity witness, or a witness about the depth actually, is that if you have these local gates as your elementary units, the depth has to scale with n in order to produce a state that has long-range correlations. So that's one example of like a sort of very simple way that you can bound, say, the depth of your circuit if your gates are local. Yeah, you got a question? I don't know where the mic went.
What would be your gate set in this example?
Well, let's suppose I just allow local gates. Like, suppose I have a superconducting circuit, all I can do are local transformations between pairs of qubits, and I want to prepare approximately some lattice-regulated field theory state. I would necessarily have to use a circuit that has a more than constant depth.
But are you considering a lattice approximation?
Yeah, let's say, let me say a lattice-regulated field theory. Yeah. Okay, but we have less understanding in this case, but we still have good ideas for how to make such things. You may have heard of, for example, a Mera circuit or a deep Mera circuit. That's the kind of circuit that can prepare this sort of thing. The rough picture is something like this. We apply, say, a finite depth circuit. I'm missing let me do this again. 2, 3, 5, 6. Like that, we apply a finite depth circuit, and now what this does is it doesn't produce a zero state out, but it, say, unentangles half of the degrees of freedom. So, for example, you start with the full state here. I'm going to go backwards. It's more convenient this way. And what you get out are, say, zeros on every other line. So half of the lines terminate, half of the lines go through, and then we can imagine applying the same kind of circuit again removing sort of half the degrees of freedom. I won't have time to go into this in any detail, but this is sort of a normalization group inspired procedure where you're kind of removing the short distance entanglement at every step, and then what's left is the infrared degrees of freedom as far as that layer is concerned. So you would sort of thin out half the degrees of freedom, then do it again, thin out half again. So you'd start with n qubits, you'd have n over 2 left here, then n over 4, and so on. You can convince yourself that the number of such layers would be log n, and this turns out to be sufficient to generate, for example, power law correlations, to generate the kind of entanglement you expect to have in a CFT, and so on. Yeah?
Excuse me, wondering if this would break the translational invariant?
Yeah, this does break the translation symmetry. Now, you can, say, variationally optimize these to get a good approximation to the ground state, and then it typically reemerges, at least approximately. But yeah, we don't have a very good ansatz that sort of does the scaling and the translation in a unitary way. That seems a little bit hard to do. But yeah, that's a kind of more detailed, it's important, but a more detailed point. Important for practical, like if you want to actually solve your lattice model, that's important. Okay, and let me give you one more example. And let me just say, you can actually estimate the complexity. If it's finite depth here, acting on n qubits, then finite depth acting on n over 2, then finite depth acting on n over 4, and so on. You can sum that series, and the complexity is actually still proportional to n. Right? So it's roughly like this. The sum from L equals 0 to log n. Let me write it this way. Log base 2 of n of some constant depth times the number of active qubits at that level, where this is equal to n over 2 to the L. And this is actually 2dn. So it's still actually constant number, proportional to n number of gates, even to prepare this CFT-like ground state. That's kind of interesting. Final example, time evolution. Let's imagine you have a state and you want to apply to it, it's on many qubits. You want to apply time evolution for some time t to that quantum state. If it's a local Hamiltonian satisfying certain nice properties, there are algorithms, quantum simulation algorithms. Let's say quantum simulation that give you a complexity to prepare this state which is less than or equal to some number times the time times n plus the complexity of the initial state. And so the physical idea, just as we discussed in this case, is that you do time evolution by just applying these layers of gates that essentially trotterize or approximate the physical evolution. There are actually better ways of doing it now than just naive trotterization, so that you can actually achieve a complexity which is no more than linear in time and proportional to the number of qubits. I'm making some assumption about the kinds of gates and about the kind of Hamiltonian and dropping some epsilons and not being super careful about that. But the basic fact that it's linear in time is more or less robust. And so what this means is that if you go all the way back here to the start, I intentionally did not erase this first board. We plug in lattice regulated n equals 4 super Yang mills. Just imagine you can do that. There's no reason why you can't. Then what this tells us is if we apply this simulation algorithm to that system, the complexity of the state can be no more than linear in time. And the conjecture that we're going to discuss next time is that it's actually equal to linear in time. That is, you really can't do much better than that in terms of shortcuts. That evolving in time is essentially the best way to prepare that state, and there's no simpler way to do it, at least not anything that shortcuts you by a growing amount of time. So there's an upper bound from this simulation algorithm. There's a conjecture in ADS-CFT say that it's actually equal to time. So what we'll describe next time is that conjecture and more about the motivation. And then on the third lecture, we'll actually prove for certain classes of systems that it is linear in time. Okay, so we'll prove the conjecture in some much simplified setting. Yeah, Vijay.
Just to make sure I've understood what the theorem is. So if you evolved a certain number of steps in time, and at each moment in time you applied a maximum of n gates here, then that's n times t.
Yeah.
So that's what I said is trivial. So that must be non-trivial. So I'm trying to understand what the precise statement is. So U of t is an arbitrary unitary operator?
No, this is the Hamiltonian evolution. Sorry, maybe I didn't say that. Just evolve with time. Imagine this is a spin chain Hamiltonian or something simple, whatever you like, but within some reasonable class. then this is an upper bound. It says we can simulate this evolution using the same space-time volume, basically. Like it doesn't cost more than linear in the size and linear in the time.
And simulate means a discretized application of a sequence of gates.
Yes. Which comes as close as you like in trace norm to the target state.
Okay, great.
Yeah. Yeah, it's a very beautiful subject, actually. Like Trotter formulas, that's how we think about it intuitively, but they actually don't give you a very good error. So you need to sort of do more gates per step to get like truly small error in trace norm. So then you consider like higher order Trotter formulas and all these other like signal processing technology, and you can eventually get actually, so this linear in time is what we all expected, but it's actually a very non-trivial thing from an algorithm's point of view to achieve that. There's various results that are ongoing, but there was something called qubitization that Lo and Chuang did, I guess, I forget how, like 5-ish years ago, maybe more, where they showed using essentially some sort of polynomials and signal processing technology that you could achieve this bound. I can send you the paper. Yeah. Oh, there was a question from Stefan here in the front.
Is there a difference between integrable systems and is there a link to quantum chaos, or is the time evolution for integrable systems less complex, or other statements?
Yeah, that's a great question. It turns out it depends on integrability. It depends on what you mean. So there's a sense in which all chaotic systems are the same, but each integrable system is like its own butterfly. So like if it's free particle integrable, then there is a bound because you just never have to wind the free particle phases by more than a certain amount. But if it's like a Heisenberg chain, I'm not actually aware, I don't think we know that there's a shortcut to doing it, right? At least I'm not aware of it. So I think it's possible that this is maybe too crude to tell you the difference between interacting integrable and chaotic. Maybe it saturates earlier, or there must be something about it. I mean, something like the form factor, for example, will tell you the difference. But yeah, I don't know exactly how to see it here. Yeah, Jeff?
If you tried to use C0 rather than C epsilon, like would it just instantly jump to exponential after a non-zero t, or is there something that stops it doing that?
Yeah, if I allow like continuously variable in time like coefficients instead of this, like if I do like a Nielsen type of thing, then no. But yeah, here I think probably it would jump typically to very high because there's all these little tails you have to get right, and they extend out arbitrarily far in the system, and yeah, I wouldn't know how to deal with those.
Nielsen would just let you simulate Hamiltonians directly, right?
Yeah, that's right. That's right. Okay, great.